Recursion is one of the most powerful ideas in programming and one of the most misunderstood. Today we'll cover what recursion actually is, why every recursive function needs a base case, the call tree that explains why naive recursion is sometimes catastrophically slow, how memoization fixes it, and finally, when recursion is the right tool, and when iteration wins. Recursion is a function that calls itself. That's it. Every recursive function has two parts. A base case, the simplest input, where you stop calling yourself. And a recursive case. Break the problem into a smaller version of itself, then call yourself with a smaller version. Miss the base case, and you get infinite recursion, which Python kindly stops with a recursion error after about 1,000 frames. Here's the classic example. Factorial. The factorial of n is n times the factorial of n minus 1. Base case. Factorial of 0 is 1. Recursive case. Every other call shrinks the problem by 1. 5 lines of code. Beautifully readable. The downside, every call adds a frame to the call stack, so factorial of 10,000 will blow the stack. Here's where naive recursion gets dangerous. Look at Fibonacci. Fib of n equals fib of n minus 1 plus fib of n minus 2. That's 2 recursive calls per call, and each of those makes 2 more. This is the call tree for fib of 4. Each node is the argument to fib. Fib of 2 gets computed twice. Fib of 1, 3 times. The same subproblems redone. Fib of 40 is over a billion calls. The fix is memoization. Cache results in a dictionary so each subproblem is computed once. In Python, you can do it by hand, or just slap functals.cache on top of the function. One decorator turns exponential recursion into linear time. This is the gateway drug to dynamic programming, which is just recursion plus memoization, dressed up. Recursion shines when the problem itself is recursive. Trees and graphs, natural fit. Divide and conquer. Merge sort, quick sort, binary search variants.
Backtracking, queens, Sudoku solver, regex engines.
Parsing, JSON, math expressions, programming languages. Anything where the structure of the data mirrors the structure of the computation. The code reads like the definition of the problem. When should you reach for iteration instead? When the depth could exceed a few thousand, Python doesn't optimize tail calls. When the problem is naturally linear, a simple loop is cleaner. When performance matters, and the recursive solution does repeated work without memoization. And when the team that reads your code will find a loop easier to debug than a stack trace. Recursion bends your brain the first time you see it, but once you can think recursively, half the algorithms in the book write themselves. Trees, divide and conquer, backtracking, dynamic programming, all built on this one idea. Thanks for watching this series so far. More topics to come, but for now, you've got a solid toolkit.